All right, the third type of solution, the first two are both acids, strong and weak. Third one we're going to talk about is bases. We're going to focus with bases just on strong versus weak. I've already told you that strong bases have to have the hydroxide component, and you'll have to use how many hydroxides are present in that particular base to figure out the concentration of hydroxide, and you can use that in your Kw value to find the hydrogen concentration, which should be relatively small. Your weak bases are going to have either ammonia or there'll be an NH2 group associated with them. And since they dissociate in very small amounts, they and water will be the two substances that are present in major quantities. So rather than using a Ka expression to find our hydrogens, we're going to use Kb expressions with our weak bases to find hydroxide, because we have to figure out the amount the base associates by. And then we will use our Kw and our hydroxide concentrations to find our hydrogen concentration and subsequently our pH. So this is kind of working backwards from what we just did with acids. So in this particular one, we have strontium hydroxide. So your two species are the strontium ions and hydroxide ions. Complete dissociation occurs. The hydroxide concentration doubles because there's two OHs and SrOH2. I can use that hydroxide concentration to calculate pOH, and then I can add that and pH together to give me 14, which will allow me to solve for the pH value of 14.18. I can also do this given a pH, use that to find the concentration of the barium hydroxide. So if here the pH is 10.5, I can use pH plus pOH to get equal 14 to find my hydroxide concentration. So that would give me 3.50. And because according to that equation there are two OHs in barium hydroxide, once I find the hydroxide concentration of 3.2 times 10 to the negative fourth, I have to account for the fact that that's counting for two OHs that are made from one barium hydroxide. And when I account for that, that reduces my concentration by 1/2. Okay. I'm sorry I'm doing these videos kind of fast. I will explain a little bit more on Monday what the heck's been going on. Okay. So 1.6 times 10 to the negative fourth would be the concentration of the barium hydroxide solution. Here we have a weak base. I know you do not have KBs on your chart for a whole lot of these ammonia-based bases, so I will give you KB values on your worksheets when you need to use them with these. So here we have hydrazine, H2N, and H2 being added to water. Because it's accepting a proton, it becomes H2N and H3+, and OH minus gets left behind. You have your K value, 3 times 10 to the negative 6, pretty small. We want to find the pH of this solution. So it's a weak base, which means it's just going to be the hydrazine and water that are the primary components in the mixture. When I add it to water, I see that it makes the two products we talked about previously, and that my Kb expression would be those two products over the H2N and H2, which is aqueous, so I'm allowed to include it in my K expression. Water still is not included because it's a pure liquid. And I can set that equal to my Kb value. The only concentration I have present initially is the 2 molar. So the two products are going to go down by 0, and are going to start at 0, which means the reactant is going to decrease and the products are going to increase. And so when I combine those together, 2 minus x, x and x, I am allowed to assume that that x in the H2N and H2 is negligible, that it's just going to be 2. So when I substitute those into my expression and solve for x, I get my hydroxide concentration, 0.0024. I can verify that the 5% rule is met. Again, you're never going to have to do this. I'm not going to give you a situation where it will not be met. This one is well under 1%, so we're good to go. So I can take that x and use that to find my pOH, 2.62. And now I can use that to work backwards to find my pH, 11.38. Alright, and I believe that's it for those examples. Yeah. That's it for the base examples. And so now you should be able to do the pH of the basic solutions worksheet. The first 3 are dealing with your strong bases. They all are hydroxides. I didn't give you the Kb value for ammonia because I know that one's on your chart. but I knew you did not have pyridine, so I did give you that one. I will give you a heads up with this particular equation. So you have C5H5N being added to water, and it should be a double arrow. Sorry. Symbol. Give me a second. Give my computer a second. Maybe if it decides to cooperate. Or maybe it won't. There we go. So if the base is accepting a proton from the H2O, then OH minus would be left behind. And so your equation would look something like this, with your original two reactants, the pyridine and the water. And then when the base accepts that proton, it becomes positively charged to become the conjugate acid, and then OH minus is left behind from the original water, which was acting as an acid. Alright, so that should get you through this worksheet.